All right, I'm going to share screen.
Like on rare occasions.
I'm not, we're not, like, we're supposed to be very accommodating this semester. So, yeah. Let's see. See, this screen sharing thing, it's always in my way. I want attendance. But it was nice to have a little break in between classes. That was kind of nice. I feel like I'm running. Okay. And then okay. Oh, here. Attendance. All right. Get the chat going over here. Yes, Abigail. I'm going to show you in just a second, Abigail. I'm going to go over all that for everybody. Just hang on. Okay. Okay. Got this going. And I need this. Okay. And the microphone. Uh-oh. Low battery. Of course it would do that. No, I well told them. I have to carry my own battery. I really do. We have AAA, but we don't have AA over here. Should I put them in there? Oh, they're good. My battery's not good. No, you can't hear because, let's see. No, I think I'm just not saying anything right now because I'm changing the batteries in my microphone. Hopefully I'm changing the batteries. Caitlin, can you hear me now? I feel like the commercial. Can you hear me now? And it worked last class period. Oh no. I carry around batteries, but they don't work. They're new. I noticed that. Put them in correctly. You've got to be kidding me. Hold on, y'all. that wasn't working. Let's see if this works. I just have to do this. Oh. Oh, y'all. The battery's dead in that too. Like this is, oh, it's on. Okay, we're gonna roll with it. When I get some batteries for this, I will, but, okay. We'll move this over. Sorry. Okay, how's that? I'll try to stay really close to the microphone. All right. So I got some things I want to cover. Okay, so first things first, what's due next? Monday at 9 p.m. homework from chapter 7, right? Okay. The next time I see you, what do we have? An exam, right? Okay, on Respondus, on Moodle, so please make sure you have a good internet connection and that you're not in the dorms. Go to a computer lab, come here. Just don't do it in the dorms. The dorms have notoriously bad internet, so don't do that. All right, on to the good news. So I've decided that I'm trying to help y'all out. And so y'all know we're scheduled to have 3 exams, right? So I have the syllabus designed, so you'll have 3 exam scores. What I'm gonna do is I'm gonna give you a 4th exam that's gonna cover the last of the material, just the last of the material, and then I'm gonna let you drop your lowest exam score. So if you have one where you had a bad day, you just drop it, right? And it also gives you an exam where you have a chance to be tested on that material without it being on the cumulative final exam, okay? So let's look at the calendar real quick. So we are here, we're right here. We're Thursday right here. Chapter 7, part 2. Your homework is due on Monday. Then we have exam 3 on Tuesday. Then Wednesday is drop day. So you'll have your exam score Tuesday afternoon. So if you're trying to make a decision on dropping or not, you can make that decision as informed as possible. Then we'll have chapter 8. Now look what happens after chapter 8. Our homework is now going to be due on Wednesday instead of on Monday. So be careful. You don't have the whole weekend right before it's due. So don't put it off until Monday night. FYI, don't do that. Then chapter 9, part 1 and 2. Chapter 9 homework due again on a Wednesday. Chapter 10, part 1 and 2, again due on a Wednesday. And then you'll have exam 4, which will be just the chapters that we cover between exams. And then your lowest regular exam score, so either 1, 2, 3, or 4 will be dropped. So if you're happy with your 1, 2, and 3 scores, I could drop your 4th exam. Whatever floats your boat, okay? Then the next week is finals week. So our finals for this class, y'all are in 5T. So 5T is going to meet right here. It is going to be a paper exam. We're going to meet right here. I guess I should type that in. Can I type that in? Oh no, I'm not signed in. I'll type it in after, but it is going to be here in the ballroom. It will be a paper and pencil exam. Okay? So make sure you come. It will be on paper here in the ballroom from 10:30 to 12:30 on Monday the 16th. Okay? All right. So if you go to Moodle, what you'll see is, right, our exam 3 here's, oh, this is supposed to be unit 4, not unit 3. Hello, come on. Okay, so unit 4, chapters 8 through 10. So that'll be 8, 9, and 10. Exam, why did I do that? Exam 4, right? And then you'll have your cumulative semester exam. And then just as a reminder, 5T, that's us, we'll take your exam on Monday, the 16th, from 10:30 to 12:30. Questions? All multiple choice on the exam. I don't have a study guide, no, for the final exam, no. What's Thursday at 1:30? Oh, that's your normal class time. This is our normal class time. If you're in 5T, you normally meet Tuesday, Thursday from 1:30 to 2:50. And so our section 5T will meet on Monday. My 4T section, that's from noon to 1:20, will meet on Thursday for their exam. Okay. Other questions? All material is fair game on the final. That is correct. So if you look here, right, our final exam, we might have a class that day. What do you mean? No, you won't have a class that day. You won't, because they schedule all the exams that way. So during finals week, you have like a unique schedule, but it will not overlap. Absolutely. So your regular exams are 100 points each. Your final exam, comprehensive, worth 200 points. Okay, so it will be a bigger exam because it's worth 200 points and it will be cumulative. But hopefully being able to drop an exam score will be a perk for you. Okay, any other questions? I think that's, do you have any tips for going and studying for the final? Practice problems, back of the book, back of the chapter, practice problems. That would probably be really good. I'll ask Dr. Smith if he has some other suggestions. He's been doing this for a while, I haven't. So I'll see if he has some suggestions. Okay, good? All right. Okay, so we have all access to our tests we took already. Yes, you do. You absolutely do. You go back and look at your exams and see what you got right and wrong. Y'all know that, right? You can go back and see every single question on every exam you've taken, and you can go back and see what you got right or wrong, and like figure it out. I don't know how to get to it. Like, I'm not a student, so you see things differently than me. But if you want to stay at the end, I can show you. I'm sure we can figure it out together. Yeah. Okay. Anybody else who wants to? I'll do that at the end of class. Okay. So, you can minimize this. Everybody checked in on attendance, right? You've done your iClicker attendance. How many people we got today? 43. Make sure you go in and do your attendance if you have not already. Okay, because the next thing is going to be some iClicker questions. Okay. You can rework the homework for practice too. That's true. That's true. Inside the MIME Lab and Mastery, I set it to where you can go back in and you can rework anything that I've assigned to you. That's a good point, Nicole. Thank you. Okay. All right, so I'm gonna move this up here. Y'all ready for some clickers? Ready to get some points? All right, here we go. So let me move this down. Okay, there we go. All right, I'm gonna stop this, start this. Which relationship is inverse? That means when one increases, the other decreases. Oh, it's not the batteries, it's that the battery thing won't close. Another day. forgot to tell y'all the joke for the day. When this one's over, I'll tell y'all joke of the day. That'd be terrible of me if I forgot. $10. So glad I remembered my jacket today. All right. So what formula did you use to answer this? Whoa. Okay. Pivnerd. PV is equal to nRT, right? So if two things are on the same side of the equation, they're going to have an inverse relationship. If two things are on opposite sides, they're going to have a proportional or the same. PRO. Proportional means if one goes up, the other goes up. Inverse means if one goes up, the other goes down, right? Okay, so which two have inverse relationships? You should have said pressure to volume, right? So D, good, very nice, very nice. 80%, that's great. Okay, y'all ready for y'all joke? I'm sorry. All right, what is the most popular surgery at the Lego Hospital? Plastic surgery. Look, it was good for y'all and it was good for my son, so I liked that one. All right. Why don't eggs tell jokes? Tell us, why don't eggs tell jokes? Jason's got one. Because they'll crack you up. They would crack each other up. That's great. That's awesome. I'm gonna have to remember that one. Okay. So we have a sample of gas in a 1 liter container at 1 atm of pressure, and it's placed into a larger container. What happens to the pressure? Ooh, 9 seconds, 8 seconds, sorry. Didn't we have 46 earlier? Y'all check in. 45, I thought it was 46. All right, so what happens? Make sure you write your Pivnerd. PV is equal to nRT. So what's going to change here if we place it into a larger container? But container size is a measure of volume. So you're going to have an increase in volume. So now the question is, if you increase volume, what's going to happen to pressure? It's going to decrease. That's an inverse relationship. So the pressure should decrease. So what did y'all say? Yay, 80%. Awesome. Pressure should decrease. Good. Okay. Now, we have a sample of gas. It is 1 liter at 25 degrees Celsius. We heat it to 50 degrees Celsius. What happens to the volume? Hayden, don't put it in the chat. Click in. Okay, 10 seconds. All right, Piv nerds. All right, PV is equal to nRT. What's changing in this one? Our temperature, we go from 25 degrees to 50 degrees. So we increased our temperature. We really increased it by double, right? 25 plus 25 is 50. So what do you think is going to happen to the volume? If they're on opposite sides of the equation, volume will increase. So an increase in volume. And it's actually going to be the same amount, right? If one side gets double, the other side has to double in order for the two sides to be equal. So the volume doubles. So what did we say? Good, B. Good. Okay. All right. This one's from your notes from section 2. What change of state occurs when frost forms on car windows on a cold morning? We got this one and one more, and then we're going to go to the ICP. And y'all tell me if I get too far away from the microphone, because I'm not used to having to stay in one place. Oh, 5 seconds. But we look, we got everybody. We got all 46. Okay, so what state of matter are we going from and to? From a gas to a solid. Very good. So that is, what did y'all say? That is C. That is C, deposition, deposition. Right? If you go from a liquid to a solid, that is freezing. But be careful, right? Frost forming on a car window, where's the water coming from that turns into the ice? Because it is ice. Did it rain? No, it was just water in the atmosphere. So it's just gas. Okay. All right. I think I said one more, right? 7? Yeah, one more. And then we're going to go to the ICP. All right. So my question to you is, what happens during vaporization? What happens during vaporization? 10 seconds. All right. So vaporization is a change in the state of matter. What state change is it? Vaporization. This one is liquid to gas. So you have to know these, liquid to gas. So two of the answer choices are asking you if it has to do with covalent bonds, and two of them are asking you if it has to do with intermolecular forces. So if you're changing states of matter, let's say you have water, and you're going from liquid water to gaseous water. Did you change your substance? No. So did you change covalent bonds? No, that's what a covalent bond, breaking and making covalent bonds make new substances. So in vaporization, we went from liquid water to ice, but we still have water. So it can't have anything to do with breaking or making bonds. So those two answer choices cannot be possible. It has to do with overcoming intermolecular forces. So if you're going from a state of matter that is ordered to one that is less ordered, so liquids got lots of hydrogen bonds that happen in it, but what happens when we go to a gas? Those molecules are like so far apart from one another, right? And so do you think they're participating in a lot of hydrogen bonds? Too far away, it's not going to happen. And so you have to overcome those intermolecular forces between the water molecules in order to allow those gas particles to move more freely, right? So our intermolecular forces of attraction are disrupted, okay? So what did y'all say? Let's see. Y'all said, ooh, good. Most of y'all said B. So y'all were all trying to say broken or disrupted, so that's the right pathway of thinking, but not covalent, cannot be covalent, okay? All right, so let's switch over. Good start. And I'm hoping that we have time at the end to get in a few more clicker questions while it's fresh on your mind and bump up your clicker question points. All right, identify the strongest attractive force present in the, we did, and I'm starting, but we did 2-4, that was our last one, functional groups, right? Yeah, okay. So then we need 2-6, which is here. All right, so identify the strongest attractive force present in the pure substance shown. All right, so in order to do this, what you want to do is you want to look at the different substances and identify functional groups that could participate in different kinds of interactions, right? So let's kind of order these real quick. What's the weakest force possible? London. And London forces occur only in what? Non-polar substances. And they occur in polar, but they're the only ones that occur in non-polar substances, right? So non-polar is only going to have London. If you're polar, you're going to have London, and what else? What's the next strongest? So these are dipole-dipole. Then what? Hydrogen bonding, which is a type of dipole-dipole interaction. It is not a bond, right? Not a bond. Then what do we have? Dipole, do you notice it's in order for you? And then what? Ionic attraction. Okay, so that's the order. And so in order to identify if you're London forces or if you're any of the other things, all of these other things only occur in polar substances. They don't occur in non-polar substances. So polar only. So look at substance A and tell me, is that substance polar or non-polar? What do you see in there? It is polar. Hayden, you're right, it is polar. What makes it polar? The OH, that is correct, the OH. So right here, our alcohol, I feel like I get too close. Ooh, sorry. Sorry, y'all. It's a struggle today. So we have an alcohol functional group. So what can that alcohol functional group participate in? What kind of interactions? What is it? Yep. Hydrogen bonding. Even though it's not a bond. Not a bond. Hydrogen bonding, that is correct. Because what do you need for hydrogen bonding? You need H, no fun. Okay. All right, let's do the next one. Let's do B, KCl. It's just KCl. It's a pure substance. Nothing else there. This is not nonpolar. Be careful. When we say KCl, what we really mean is that we have this ionic solid that looks like this. And every other one is positive, negative, positive, negative, positive, negative, positive, oh, that was negative. Negative, positive, negative, positive, negative, positive, right? And so overall, this whole thing has a net charge of 0. But tell me about the individual atoms. Tell me about, if this were KCl, tell me about K. What is K? K plus, Cl minus, right? These are ions. So what holds a potassium atom to a chlorine atom? Their attraction to each other, right? Because one's positive, one's negative. So what is that? That is called ionic. Yes, it's an ionic bond, so it has an ionic attraction. That is correct. The ionic bond is the actual exchange of the electron, but once the electrons have been exchanged, why is it held together? Because the electrons moved on. It goes to the negatively charged ion. So why is an ionic compound held together? Because of those opposite charges. That's what holds the solid together. Okay. All right, C, CH2Cl. Would it help if I drew it? Come on. Okay. So this is a polar molecule. Who's the most electronegative atom on the periodic table? Fluorine the floozy. Guess who's the next door neighbor to fluorine the floozy? Chlorine, also a halogen, right? So they're very close to one another. So chlorine is going to be electronegative. So that's going to be an electronegative bond. Do we have a polar bond between carbon and hydrogen? No, we said that's 0. So we don't have bonds on those. We don't have polarity on those, but we do have polarity on this other carbon chlorine. So what's my overall dipole moment? Looks about like that. So do we have a polar molecule? Absolutely, we have a polar molecule. Can this polar molecule participate in hydrogen bonding? It's got hydrogen. It cannot participate in hydrogen bonding. It has the hydrogen, but the hydrogen is not attached to a nitrogen, an oxygen, or a fluorine. So it cannot participate in hydrogen bonding. So what is the strongest interactive force in CH2Cl? It is dipole-dipole. Dipole-dipole, good. Okay, this last one right here. What do we think? Do we have any polar bonds? Yeah, we do. We do, right? What's my polar bond? My polar bond is between oxygen and carbon. So oxygen's more electronegative. It's closer to fluorine on the periodic table. So we got an oxygen, we got hydrogen. Are we going to participate in hydrogen bonding? Do we have a hydrogen bound to no fun? No, we don't. So we do not have hydrogen bonding. That is correct, you guys. No hydrogen bonding. So what kind of interaction is strongest in this molecule? Dipole-dipole. Now, if they asked to list all of the interactive forces, you would have had to list London dispersion for all of them, but they didn't ask for that. They only asked for the strongest. So be very careful when you're taking the exam that if I say strongest, you give me strongest. If I say what are all, then you also have to give me London dispersion, okay? So be careful with that.
Can you explain ion dipole?
Ion dipole is like if you had this molecule right here, right? And what if you also had a sodium ion? So these electronegative areas of the molecule would want to interact with this positive ion. So it's between one ion and between a molecule that is polar. Good? All right. Okay. Now, we have to talk specifically about hydrogen bonds. So how many hydrogen bonds can CH2O make to water? Draw them. All right. So let's draw our CH2. So how would I draw that? Carbon's going to kind of be in the middle. And then how many different things do I have bound to the carbon? 3 different things. So it'll be kind of a triangular shape, right? So I have to have a hydrogen and an oxygen. 2 hydrogens and an oxygen. Does everybody have a complete octet? Nope. Who's not happy? Carbon not happy, just complaining and complaining. Now are we happy? Carbon is, but not oxygen. Tell me about oxygen. Needs 2 lone pairs. Good. All right, now, is this molecule going to interact with water? Yeah, absolutely, absolutely. Okay, so if I have water, what part of water is going to interact and what part of this molecule is going to interact? Yep, so our hydrogens are going to be donors. And then, so this is going to be a donor, and this is going to be an acceptor. And so we just draw kind of a dashed line between the donor and the acceptor. So why is it that we could say CH2O is making hydrogen bonds in this case when before, this is a polar molecule, it doesn't have hydrogens attached to oxygen. So how are we participating in a hydrogen bond here and we weren't earlier? Because we're not a pure substance here. We have 2 different kinds of molecules here. We have water, we're with water. We have water and we have our CH2O. Up here, if I scroll up, They said between the pure substances, so there's no water around. That can be somewhere that trips you up too. You have to know, are you talking about an interaction in a pure substance, or do you have that substance with water? It's two different things that could happen there. Okay. All right. Is that the only hydrogen bond? No, it's not. I have another lone pair, right? So what am I going to do? I have another donor and another acceptor, right? And then try the thing. So this is my donor. This is my acceptor. So acceptors are always going to be what? Lone pairs. And because they're what? Partially negative, right? How about donors? Hydrogens, because they are what? Partially positive. So it's the partial positive attracting to the partial negative. So, oh, how many did we make? 2. Okay. All right, now, predict which pure substance will have the lower melting point, baking soda or phenol. Explain your answer. All right, this is one of those things that you need to write on your scratch paper before you take the exam. Like you do your environmental check, right? You get a blank sheet of paper. It says start your exam. Write this down. All right, what happens as we increase the strength of interactive forces? I-N-T-E-R, that's supposed to be T. Interactive forces. What happens? The stronger the interaction between any two molecules, the harder it is to break them apart. So let's say that you have a liquid. Let's say that you have water, right? Water has a really strong hydrogen bonding attraction to itself. So how easy is it to break it? It's not very easy at all. And so it takes a lot of energy. You have to get to 100 degrees Celsius in order to boil water. So if you have a high strength of interactive forces, that's going to mean that you have a high boiling point because it's difficult to break those bonds. Well, the same thing is true about a melting point, right? If you have a strong attractive force to one another, you're not going to want to go into a liquid form. You're going to want to stay as a solid for as much as possible. And so you end up having a high melting point. How does that relate to vapor pressure? Because these are our 3 things. I know it's not in the question, but our 3 things: boiling point, melting point, and vapor pressure. What happens to vapor pressure as we increase the strength of our interactive forces? It's going to be the opposite. It's going to decrease, right? Because if you have a high boiling point, that means not much of your substance is turning into a vapor. And so what vapor pressure is all those particles that are in the air that are pushing down on the liquid. And so if you have a high boiling point, not much is going to turn into a gas. So you're not going to have a whole lot of gas. So you're not going to have a whole lot of pressure pushing down on that surface, right? So boiling point and melting point are the same. Vapor pressure is opposite. So like, get your paper, write that down. You know how you ever notice how I'm like telling you things to write down for your exam? It would be really good if you wrote them down. That way you weren't going through the exam trying to figure out, okay, let me remember what it is after I've already read a question and I'm kind of confused, right? Okay, so now we have to make our prediction about baking soda and phenol. Tell me about strength of bonds. NaHCO3. What could you tell me about what's going on in that molecule? NaHCO3. I tell you that's Na plus. HCO3 is a polyatomic ion with a negative charge. What kind of interaction is going on there? Close. Close. Do you remember how when we said if you're going to write an ionic compound, you're going to have a metal and a non-metal, or what? A metal plus a or a polyatomic plus a polyatomic, right? It just has to be, these have to be positive and these have to be negative. Remember that? So now tell me, what kind of an interactive force exists in this pure substance? We have an ionic compound, ionic attraction. If you have an ionic compound, you have ionic attraction. Okay, how about phenol? What do we have in phenol? We have an alcohol or a hydroxyl, whichever one you want to say. So if we have a hydroxyl, what can happen? Hydrogen bonding. Always, always, always with a hydroxyl, because you have hydrogen down to no fun, the oxygen. Okay, now we've identified our forces. Which pure substance will have the lower melting point? The lower melting point is going to be the phenol, right? This has a lower force. The lower the force, the lower the melting point. Okay. What's next? Okay, so this is going to be fun. Rank the following compounds in order of increasing boiling point, lowest to highest, and explain your ranking. All right, to do this, let's do this. We want to go in order of increasing boiling point. So we're going to go from low boiling point to high boiling point, right? So tell me about the forces. If you have a low boiling point, are you going to have strong or weak forces? You're going to have weak forces. And we want to go all the way over here to something that has strong forces. So let's label our molecules A, B, and C. In A, anybody recognize the functional group? It is an ester. It is an ester. It's an oxygen bound to 2R group, so that is an ester. And we know to complete the octet, we need to have those lone pairs on our oxygen. How about B? What is B? That's an alcohol. So to complete our octet, we're going to give those oxygens some lone pairs. And how about C? A straight chain alkane. Okay, so let's talk about the forces. In A, what kind of forces do we have? Be careful. Do we have a hydrogen bound to no fun? It's okay. It's okay. We have the oxygen, we have the acceptor there, but we're in a pure substance, so we don't have a hydrogen donor, right? So what kind of interactive forces do we have? That is correct, dipole, dipole. Because we know this is a polar molecule. Think about water, right? Y'all know this is the structure of water, and you know that water is a polar molecule, right? How do I change water into my substance right there? I just say, well, let's just make those carbons. Do I still have a polar molecule? Still polar, okay? All right, in B, what do we have? Yes, we have hydrogen bonding. I just love hydrogen bonding. I just love me saying it's not a bond, right? Okay, and then in the last one, what's our strongest force? London. Sometimes they call it London dispersion because it's all about dispersing the electrons. All right, so weakest forces. What's the first one with the weakest force? A, B, or C? C, then what? Then A, and then B. If you identify what's there and what interactions are happening, and then try to order them, you're better off than just trying to do it all in your mind. Okay? All right. Two common inhalation anesthetics, desflurane and halothane, have boiling points of 23.5 degrees Celsius and 50.2 degrees Celsius, respectively. Which one is predicted to have a higher vapor pressure at a given temperature? So I'm going to write my little cheat sheet, right? Stronger, stronger is what? A high boiling point, a high, and a. Okay. All right. So which one is predicted to have the higher vapor pressure at a given temperature? If we have desflurane at 23.5 degrees Celsius boiling point, and we have, what's the other one? Halothane at 50.2, that's our boiling point. So if this one has a higher boiling point, it's going to have the what? Lower vapor pressure. So this one has a lower boiling point, and therefore we'll have a higher vapor pressure. See why it's really nice to write that thing on the side? All right, now we're going to take intermolecular forces a step further, and we're going to talk about how they determine solubility. So in order for something to be soluble, it has got to be completely surrounded by water. That's the deal. So how do you make that happen? Well, we know to make hydrogen bonds, you have to have polar functional groups, right? We just saw that. So you want to have as many polar functional groups as possible, but you also want to have those functional groups kind of dispersed throughout the entire molecule. So you don't want them all on one end, because if you put them all on one end, then one side is going to be polar and want to interact with water, and the other side not. And so what do we call that? Any takers? You have one side that's positively charged, one side that's charged, and one side that's non-polar. So a polar end and a non-polar end. Amphipathic. So a micelle forms because you have an amphipathic molecule. And the amphipathic molecule means you have a non-polar end and a polar end. And so if you have a bunch of them get together, right? Well, then the charged areas are going to want to interact with one another and water. And then the polar ends are going to stick out and not want to hang out with water, right? So how do they form? They end up forming that micelle. So if you have a charged end and then the polar groups, right, what's going to happen? Or really three. They end up forming like this. Really cool. Looks like this, right? A beautiful drawing. I know y'all are impressed by my drawing. I know. But this is how soap works, right? You have dirt in the middle. Dirt's nonpolar. So the nonpolar parts of the molecule are going to want to interact with dirt. The polar molecules are going to want to interact with water, right? And then this all goes down the drain. You never think about washing your hands the same way again. Now that you understand that, right? Totally cool. All right, and I just drew all over a question. All right, based on their polarity and attractive forces, predict whether each of the following compounds are soluble, insoluble, or form a micelle in water. All right, NaCl. What is NaCl? It's salt. Y'all, does salt dissolve in water? Salt dissolves in water. I want you to use your common sense in addition to what you're learning in class, right? Because that's going to give you some clues. So if salt, you know salt dissolves in water, you know sugar dissolves in water, right? So keep those things in mind when you're doing this. But the question is why? So it's soluble. It's soluble. Why is it soluble? Remember what we drew just a few minutes ago, right? And we had the negative and a positive and a negative and a positive, right? You remember this? So what's going to happen when this interacts with water? Water is going to end up surrounding the positive. The oxygen is going to want to hang out, right? Because the oxygen is partially negative. So on and so on and so on. And then how about the negative particles? Our hydrogens are going to want to hang out with that. Oh, it's a drawing day today. Okay? And so water is going to surround those individual atoms of each of the ions, and that's why it dissolves. That's how it works. Okay? So it's very soluble. Very soluble. Sodium stearate, a fatty acid salt. What is a fatty acid salt? It's a what? So a fatty acid is a long chain. That's exactly right. So if we draw a long chain, let's see. What does our chain end in? It's the fatty acid. A carbonyl group bound to an oxygen, right? Now, if it's a salt, that means one thing must be negative, one thing must be positive. So instead of having a hydrogen there, it's a negatively charged oxygen. And so this part of the molecule is polar. And this portion, and it can go very, very long, right, is non-polar. It's just non-polar. So what's going to happen? Micelle is going to form a micelle. Absolutely. Okay. How about isopropyl alcohol? Right, that's CH3, CH coming off of that H is an OH and a CH3. What do we have on that oxygen? Lone pairs. Oh, look, no fun. We have hydrogen attached to an oxygen. Yay, no fun. So what can this participate in? It can hydrogen bond with water. If it can hydrogen bond with water, is it soluble? Yes, soluble. Right? Remember the golden rule of solubility is like dissolves like. So water is polar. If you want to know if something's going to dissolve in water, is it polar? If the answer is yes, then it dissolves. NaCl is an atom of Na, an ion of Na, polar. It is charged, so yes, so it will dissolve, right? But our fatty acid salt, we have this huge non-polar section, so it's not going to be soluble. Okay. All right. We're getting close to the end. Not too much left. All right. Predict which of the following compounds is likely to be more soluble in water. Justify your answer. So in A, I'm going to be like the eye doctor. You ready for this? 1 or 2? 2 or 3? No, 1 or 2. You can only pick between 1 or 2. Which one do you think is more soluble in water? 1 is more soluble in water. Why? It has our alcohol, which can what? Water. Good. Yes. Yes. Okay. For B, 1 or 2. So what do we say? Anybody else? 1. Okay, so what does 1 have? Not only does it have an H, because 2 has an H as well, but it's with nitrogen, it's with no fun. In H2S, the hydrogen is attached to a sulfur, and sulfur is really no fun, right? Because it's not part of the no fun. So in CH3NH2, you have a hydrogen attached to a nitrogen. So you can participate in hydrogen bonding. So because it has hydrogen bound to nitrogen, so can hydrogen bond with water. Yeah, I'm telling you, I need to practice these. Until you practice and don't have somebody next to you giving you the answer, you know, you think you might know it, but go to those practice problems at the end of the chapter and make sure that you can identify things that make something soluble or non-soluble. Just takes practice. Okay. Yeah, there we go. All right. So now, when we, oh wait, did I go too far? I know, that's what I was thinking. I think I skipped some. Oh, this thing is just, that was 12. Oh yeah, I should have scrolled down. Okay. All right. So now we're talking about lipids, dietary fats, right? What component molecules make up a triglyceride? So what does the tri refer to? 3, well, it's not actually 3 carbons. It does have 3 carbons. You're right, it does have 3 carbons. But the tri refers to the number of fatty acid tails, right? And then the glyceride refers to glycerol, which has 3 carbons. So that means you have 1 tail per carbon. So a glyceride, glycerol, has 3 carbons. It has some hydrogens, and they're bound to an oxygen, right? So let's give it enough hydrogens to be happy. Nope, that was wrong. This is a 2. This is a 2. So normally in a glycerol, this would be an OH, right? But because it's in a fatty acid, it doesn't have a hydrogen, and instead it's attached to the fatty acid tail. So that oxygen there is then attached to the carbon in the carbonyl bond. And then how do you make up the rest of the fatty acid? Chains, right? And who knows how long it is, but let's just give it a good tail. It's not that, I found out it's not this, it's that, oops. No, you're fine, it's okay. It's fine. It'll only stay on if you hold this down.
Is it because of the batteries?
No, I put new batteries, because I had that, I brought a pack, and they're AAA. It's okay.
It
It's
was
okay.
behind there or something. Okay, I'll get some more.
So, no, yeah, so I had an extra set in my bag, but, so, like, just some duct tape.
You can also get another. I have more of these.
Okay.
Using this right now.
Well, no, I was using that.
Do you want to wait till next time or would it be?
Oh, next time.
I'll just
Next time.
replace that.
Okay.
Thank you.
Thank you. No, you're fine. You're fine. All right, y'all. Okay. So we got a triglyceride, right? So the components that make up a triglyceride are 3 fatty acid tails and a glycerol molecule, right? Y'all are so patient, so awesome. All right, so olive oil is a monounsaturated oil. Okay, stop the train. What does monounsaturated mean? Okay, only one what? That's true, mono is one. What is saturated? Saturated means covered in hydrogens. So if you are unsaturated, what are you? You don't have all the hydrogens. So how are you going to have a complete octet? How are you going to be happy? You're going to have some carbon-carbon double bonds. Okay? So monounsaturated tells us how you have one what? Carbon-carbon double bond. Good. Okay. So olive oil is a monounsaturated oil with a melting point of -6. Soybean oil is a polyunsaturated oil. What does that mean? Many carbon-carbon double bonds, right? Explain their difference in melting points. So if you are unsaturated, I'm sorry, not if you're unsaturated, if you're saturated, right? You have these chains that end up aligning so nicely, right? And so you have lots of surface area contacts. What does that result in? Lots of what? London dispersion forces. I should spell that out. London forces. If we have lots of London forces, what can you tell me about the boiling point of a substance? It's going to be what? Remember, if we have, right? So if you have strong bonds, strong interactions, you have what? High melting point, high boiling point, low vapor pressure. That was supposed to be a B and a P, boiling point, okay? So if we compare an unsaturated, just a mono, that means it's going to have one double bond and then go in, right? So you're going to have some overlap, but it's not going to be quite perfect. So you're going to have less surface area contacts, right? So you have fewer London forces. So tell me how they're going to compare. The more forces you have, the harder it is to overcome the interactions. And so you're going to end up with a high boiling point. So what happens when we go to an unsaturated? We get a double bond in there. They don't line up quite perfectly, so we reduce the amount of forces. So what's going to happen to our boiling point? Is it going to go up or going to go down? You have fewer forces holding it together. So it's not going to take as much or as high of a temperature, so it's going to have a lower boiling point, right? Now, I really want to extend this page, and it's going to break my heart if I can't. Nope. I guess you can't do it in this. Can you? I don't know. Okay, so what if you had something, I'm going to erase this one, y'all have it. I'm going to erase this one. So what if I had something that was polyunsaturated? Right? Then I'm going to have lots of double bonds, and it's going to get really weird and angled awkwardly, right? Y'all, my drawing skills today are off the charts. What happens to our surface area interaction? We get even less, even less surface area, EA. So you have even less London forces. So tell me about the boiling point. Very low boiling point. So my polyunsaturated is going to have a melting point of -16, which is lower than my monounsaturated, which was -6. Does that make sense? All right, let's see. 13, we're almost done. Almost. One of the main triglycerides in palm oil is tripalmitin. It contains 3 fatty acids with carbon designations of 16-0. Draw the structure, and would you expect this molecule to be a solid or liquid at room temperature? So tell me about this 16-0. What is the 16? Number of carbons. What is the 0? Carbon-carbon double bonds. So before we even draw the molecule, can you make your prediction? Is it going to be a solid or a liquid at room temperature? Are we saturated or unsaturated? We're saturated. If you have a saturated fat, tell me, are you going to be a solid or a liquid at room temperature? All those chains are going to line up real nice and neat. You're going to have lots of surface area contacts, lots of London forces, and therefore you will be a solid. You will be a solid. Like butter. Butter is a saturated fat. Okay. So if it's a triglyceride, I'm going to start with my glycerol. And then I'm going to connect it. I'm going to connect it to an oxygen. And then I'm going to connect that oxygen to a carbonyl carbon that has an oxygen attached to it. So there's my carbonyl carbon, oxygen. All right, now I need to draw this chain to be 16 carbons long. The trick is to remember that this carbonyl carbon counts. Okay, so that's 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16. So let's go back and count and make sure. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm good. Okay, so then I'm just going to go back and do it for the rest of them. So that's 1, 2, 12, 13, 14, 15, 16. Same thing. 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16. So why did I start my numbering all the way over here? Because if you were told that this is, if you were given a number, if you were told what carbons, you would be told that it's at carbon 6, right? So then that would be a double bond between carbon 6 and 7, not between, what is this? 1, 2, 3, 4, 5, 6, not there at 11. It would be between 6 and 7. So be careful about that and make sure you number them going the right way. Okay. All right, I think the last one. All right, last one. So draw a possible hydrogen bond between a molecule of cholesterol and a molecule of water. Cholesterol is in what classification of molecules? Anybody? Any takers? It's a steroid. It's a steroid. So our steroids make up all of those different kinds of hormones and things like that, and cholesterol. And so all of those steroids have a common structural feature to them, and they're called a steroid nucleus. And it's a bunch of rings. Now you're not going to have to draw it for the exam, right? Because the exam is multiple choice, but it's a bunch of rings. And so then you have another ring. And I'm not the world's best drawer, so you'll have to kind of forgive me. And then the last one is a house and not a, right? That's what I call it, a house. And then, so this is, if I do this, this is your steroid, one double bond. That's your steroid nucleus. So everything that is a steroid has that common feature to it. Now, cholesterol is something special. Cholesterol has one polar group. It has a hydroxyl. And then it also has a really branched, funky chain of hydrocarbons. So what do I know about branched hydrocarbons? They're very non-polar, right? So you're going to find cholesterol inside of your cell membranes, and it'll change the fluidity of your membrane. Membranes are really, really cool about that. And so this non-polar part is going to want to sit in between the lipid bilayer, where you have all those non-polar fatty acid tails, right? But look over here at the bottom. What do I have down here at the bottom? Which I shouldn't have put way down there, but what do I have? I have a functional group. I have an alcohol, right? So this alcohol can participate in hydrogen bonding. So how is it going to participate in hydrogen bonding? Well, I really have, right, if I want to draw it out, I really have my hydrogen attached there, and I've got 2 lone pairs on the oxygen. So how many possible hydrogen bonds? It only told you to draw 1. But how many are actually possible? Try again. Not 2, 3. Because I have, this is an acceptor, this is an acceptor, and this is a donor. Okay? So if I wanted to draw my interaction with water, I would need a water donor. So my hydrogen bond would look like this, 1, 2, 3 little dashes, right? Same thing if I want to do another water molecule. I guess I shouldn't have drawn this there, but, right? Do another one. And then this one is going to want to interact with the oxygen. And I shouldn't have drawn that so close, but it's there. So 3 hydrogen bonds. Have y'all ever seen like an animation of the cell membrane? Okay, I see, like I should have brought y'all this, but the cell membrane is, they call it the fluid mosaic model, because if you've ever seen it, so you have this surface that looks like a solid, and it's not. It's got cholesterol in it, it's got proteins in it, and the proteins kind of like float around and zoom around. It's really cool. So that's why they call it fluid mosaic. But it's really cool. If you just Google fluid model of the cell membrane, you can see it. All right, so I guess that ends us for today. I thought we were going to get a few more clicker questions, but we did not. So next time I see you, it is an exam day. Good luck studying. Get your homework done. And let me know if you have any questions. You're good to go. Will all homework from now on have bonuses? Yes. Yes. I kind of like them. I like that they're tutorials. How do you like the tutorial bonuses? Have y'all tried them? Yeah, no? Bonuses are good, right? Yeah, they will. Y'all have a good rest of your day. Anybody in chat have anything else? I'm going to go ahead and end the Zoom if there are no other questions. Okay, if you're on Zoom and you have a question, just send me an email. Yeah, that's what y'all want to know? Yeah. Okay. Put your stuff up. Okay, so go to, you do it. Go to the exam. Yeah, so, yeah. Okay. You grade, no more attempts are allowed. Review. You see every single question.
Thanks.
Yeah.
Okay, so I emailed you this morning, but
Okay. No.
So, I think I was confused. Like this one, it can't bond because it's not bonded, so no bond.
Right.
Okay,
Exactly.
and then this one, this hydrogen can because it is bonded to an oxygen.
Because it is bonded to an oxygen. It's bonded to this oxygen.
Okay.
It's covalently bonded to a oxygen, so then it can participate in a hydrogen bond with a lone pair on a different oxygen.
Okay, so basically we just drew this water molecule because it can be bonded to this one.
Correct.
Okay.
Correct, because we basically said it in water.
Okay. That makes sense.
Awesome.
Okay. Thank you.
Yeah.
Sure.
Okay. Okay. I have it. Wait, I have it. I can help you with that. That's good. No, I'm not saving the changes. Okay, let me go and find that. That was chapter 6. My clicker questions. And I think that was the last one.
It's just a small part.
Yeah. Well, and especially if you've not done blood types before. Blood types can be confusing. Okay.
I think you said AB to give blood. No, type A to give blood to AB. I bet you can't do that.
You can. Watch. Let me show you. Oh, I didn't end this. I meant to end this.